All right, well, this is it. Our last set of new notes. My last video to record for you guys, unless I record one going over homework problems. But this will be the last video of new material. And so the idea here tonight, or today as you're watching it, is what if we wanted to add up a sequence, thus a series to infinity, right? So what if we wanted to find the sum of an infinite series? So if you think about it, this is only going to work in certain situations. If you were to try to sum up an arithmetic sequence to infinity, that's not going to happen, because if it's arithmetic, then it has a constant difference, which means that the term that you're adding on just keeps getting bigger and bigger. And so we say that that is a divergent series, because it would just get bigger and bigger and bigger as you tried to add to infinity. And furthermore, for some geometric, they are also going to be divergent, because if our ratio is bigger than 1, then obviously the number we would be adding on would be getting bigger and bigger and bigger. And so same thing, we say that that is a divergent series. However, there are some geometric series that when we add them to infinity, we actually get a finite value. So let's take a look here, for example, at this geometric series. So it says, can you add up the first 20 terms, right? So the sum of the first 20 terms would be the first term, 64, 1 minus r. So r in this case is a half, right? So if I look at this series, it's each term is a half the previous one. So 1/2 raised to the 20th all over 1 minus a half. Okay, so definitely going to need our calculator today here. So let me, whoop. Oh my goodness. Why does this always not work well when I'm doing it on here? There we go. All right, so 64 times 1 minus, I'm going to do it as a decimal, 0.5 raised to the 20th. All right, close that parenthesis. And then we're going to divide all that by 1 minus 0.5. And so I get about 127.9999, right? So if I add this up for 20 terms, I get 127.999. Well, then it says, well, what if you added it to 21 terms? So if I come in here and I just change this up here to 21, right, nothing else changes, right? The first term is still 64. The ratio is still 0.5. So the only thing that's going to change is if I go 21 terms. So notice again that this is 127.9998, right? So if I change this to a 1, oh, it's 127.9999. So as you can see, right, going from terms, adding it up from 20 to 21 barely changes our series, okay? So, right, what do you notice? Well, because the number that you added on was so small, it barely changed the sum, right? So the sum of the first 20 and the first 21 is slightly different, but not much. So then you could see that if you went to the 22nd term, it's barely going to change, 23rd term. And so imagine if you were to go to infinity, right? If you were to add this to infinity, then as you go to infinity, it is going to be a very, very, very small change. And so what ends up happening then is that we say that this is a convergent series, meaning that it will indeed add up to a finite number as I go to infinity. Now what's interesting is if you stop, then it actually doesn't add up to that finite number. You have to add it to infinity. It's kind of like 0.9999999 is not 1, but 0.99999999999 forever is 1, right? So it's that subtle difference there, but an important one. Okay, so let's just take a look down here. Sometimes, right, we deal with sequences that are infinite in length. Okay, so we asked to sum up an infinite series. And so the way we write this, right, is if the absolute value of the ratio is greater than or equal to 1. So that another way of saying that is that r is greater than or equal to 1, or r is less than or equal to -1. Okay, this is writing with the absolute value around the r. Is just a fancy way of saying for r values that are bigger than or equal to 1 or less than or equal to -1, then it is going to be divergent. Okay, I guess I could put that down at the bottom there. But if you were to plug in, right, first 100 terms, 1,000 terms, 5,000 terms, it's just going to get bigger and bigger and bigger. And so we would say then that it is divergent. But over here, when it says the absolute value of r, is less than 1, that is saying for r values between -1 and 1. All right, so if you look at this one here, the r value is -1/3. Right, over here it was 3/2. And so in this case, if I were to sum up this series, right, from 1 to 100, and then I do it again from 1 to 1,000, and then I do it from 1 to 2,000, the answer that I get is practically the same, right? So we could come in here again to our calculator. Let's go ahead and do a couple of them here. So, right, if I did the same formula again, so this time though, my first term is 1/3, right? So 1/3, and my ratio this time is -1/3. So I'm going to put that in parentheses. -1/3. There we go. And then, so if I were to raise that, right, to the, let's do 100. And then down on the bottom then, 1 minus -1/3. Right, so if you add up the first 100 terms, right, so the first term is 1/3, 1 minus the ratio of -1/3, and you're doing it 100 terms, you get 0.25. Right? If I were to go and do the first 1,000 terms, oh, I get 0.25. If I were to do, so why is that? Right? Well, it's because the calculator has decided to start rounding, right? So the problem is that the calculator at some point decided, well, it's close enough to 1/4, we're just going to call it 1/4, right? So if I were to come back in here and say maybe, yeah, so 10, right? If I go 10 terms out, notice it was already at 0.24999. So obviously by the time I got to 100, it was so close to 0.25 that the calculator just called it that, right? So in every one of these then, the calculator just went ahead and said, oh, this is 0.25, 0.25, 0.25. So we say then that it's convergent. Okay? So the main thing is, right, that in order for an infinite series to be convergent, it has to be a ratio from -1 to 1. If it's not, then you just say it's divergent and you're done. Okay, so here's the key though. The interesting thing is that our formula, right, so our normal formula, which is S sub n, is the first term times 1 minus r to the n all over 1 minus r, is actually going to simplify greatly. And the reason for that is because if r is between -1 and 1, then when I raise that r value to a really big n, right? So remember that n is headed to infinity. So as n gets really, really big, right? If I take something like 1/3 and I raise it to some gargantuan number, then the value that I get is really, really tiny. And so what ends up happening then, right, is that this part goes away. It gets closer and closer to 0. And so our formula then, when I add to infinity, simplifies And so the sum, when I add to infinity, is actually much simpler, right? It is just the first term, g1 or a1, whatever you want to call it, on the top, and then the bottom is just 1 minus r. So anytime I want to add to infinity, the formula is actually a lot easier. But of course, if r is greater than or equal to 1, then it doesn't have a finite sum. Okay? So the first thing is always just to determine if it says sum to infinity, can you actually sum it to infinity? Okay? So let's take a look here. So if I look, what's happening here in 4a is that, so what's my ratio here? It looks like it's multiplying by 1/2 every time, right? So r is a half. Okay, so that means that it is going to converge. So if I want to know what it converges to, then the sum, as this adds to infinity, is just going to be the first term, -5, divided by 1 minus the ratio, which is a half, right? So it'll be -5 divided by a half, so -10. Right? So there's letter A. So this series right here, as it adds to infinity, is going to add up to -10. In part B, so in part B, if I look to see what's it being multiplied by each time, in this one, so in B, my r is, so it's going to be negative because it changes from negative to positive to negative. So I'm multiplying by a negative each time. In the numerator, I'm multiplying by 3. And in the denominator, I'm multiplying by 2. So that means that r is less than -1. So this one is divergent. And so we're done with that one. And then on the last one there, using sigma notation again, right? So in this case, it's saying start when n is 0. So when I plug 0 in, 0.8 to the 0 would be 1. Right? So that means that my first term is 1. So again, notice that in this case, the first term is actually when n is 0, but we would still call that the first term, right? And so then when I plug in 1, I would get 0.8. So my second term is 0.8. Right? So what's happening is I'm just multiplying by 0.8. So that means that my r value is between -1 and 1. So it is going to be convergent. So my formula then to sum to infinity is going to be the first term on top, so 1. And then on the bottom, 1 minus the ratio, which is 0.8. So that's going to be 1 divided by 0.2. Right? 0.2 is 2/10, right? Which is 1/5. So 1 divided by 1/5 is 5. So that one's going to add up to 5. So even though we're using a sigma notation all the way to infinity, that's only going to add up to 5 as I go to infinity. All right. Next one, if I take a look at this series, first thing to do is check and see if it's geometric, and check to see if r is indeed between between -1 and 1. So if I take a look at this, if I think of 2 as being over 1 there, right? The top is being multiplied by 2, and the bottom is being multiplied by 3. So that is indeed between -1 and 1. So this one is going to converge. Right? So first term on top. So if I want to sum this to infinity, my first term is 2. The bottom is going to be 1 minus the ratio, so 1 minus 2/3. Right? So that's going to be 2 divided by 1/3, which is 6. So just like that, sums to 6, done. So summing to infinity is actually very simple. It's just a matter of determining whether you can do it or not. All right. And so one last kind of cool application here. Can you write 0.47 repeating as a fraction? So I'm actually going to come down here real quick. And then there's a few for you to try there. So 0.47 as a fraction. Well, if we think about what that means, this is 0.47, right? 47, 47, 47, dot, dot, dot. Right? So another way to write that then as a infinite series is this is 47 100ths, right? And then this 47 is 47 10,000ths. And then this next one right here would be 47 1 2 3 4 5 6, right? So 1 4 5 zeros, right? So 100,000ths, right? So each time we're just adding on 2 more zeros, right? So if I'm at the tenths, hundredths, tenths, hundredths. Oh wait, I left one off there. Sorry. There we go. 10,000ths, and then this one would be 100,000ths. No, millions. Well, it would help if I could count tonight. There we go. 1, 2, 3, 4, 5, 6. There we go. Millions. All right. So what am I doing each time? Well, as I go through this, right? So tenths, hundredths, and then this one's going to be 1,000, 10,000ths, right? And then this one's going to be 100,000ths, millions. So what's actually happening is I just have a ratio here of 1/100th, right? Every time I'm just multiplying by 1/100th. The numerator is staying the same, but the denominator is adding on 2 zeros, right? So if this is then really an infinite series, then the sum, as I add to infinity, is going to be the first term, which is 47 100ths, divided by 1 minus 1/100th. So that would be 47 over 100. And then on the bottom, then this would be 99 100ths. So this would be 47 99ths. So that's what that is as a fraction. So go back to earlier in the year, right, when we had our wonderful discussion. 0.9 repeating is indeed 1, right? So we proved that a couple different ways. One way was we said, well, 1/3 is 0.3 repeating. So if I add up a third, and a third, right, that would be 3/3, which is 1. Or I could add it 0.3 repeating plus 0.3 repeating plus 0.3 repeating, which is 0.9 repeating. So 1 must equal 0.9 repeating. They are indeed equivalent, right? That was one way we did it. We saw it another way. We said, what if we call 0.9 repeating x? Then if I multiply both sides by 10, that would move the decimal, so I'd get 9.9 repeating equals 10x. Right? So then if I subtracted the equations from each other, then I got 9x equaled 9. So x was 1, but x was 0.9 repeating. So by the transitive property, 1 and 0.9 repeating are the same. Oh, there goes the cuckoo clock. And then our last way to do it is using our new formula. So 0.9 repeating can be written as an infinite series, right? This is 0.9999999. So this is 9/10ths plus 9/100ths plus 9/1000ths plus forever. So each time it was getting multiplied by 1/10. So my ratio is 1/10. So if I sum this to infinity, my first term is 9/10ths, and the bottom would be 1 minus 1/10. So that would be 9/10ths divided by 9/10ths, and by golly, that's 1. So 0.9 repeating is 1. So there you go. That's a fun way to finish out the year of notes. Yet another fun way to prove that 0.9 repeating is indeed 1. So boggle your family's minds with that. That's fun stuff. That's cool math. And I will hopefully get some questions this week and can answer those, so this won't be the last time you hear my voice. And then hopefully you also saw that I would love to have a little checkout with you guys next Monday. I know that technically school's over Friday, but that way you guys are taking your quiz and stuff on Friday. So that way on Monday, I'd love it if you could pop in to one of those 2 times. on that Monday. Originally, I had 3 o'clock as one of the times, but I actually moved that up to 2 o'clock next Monday. So either at noon or 2 o'clock, you could pop in and say goodbye. That would be great, and I'll give you some free points for stopping in. Maybe a little incentive there, but I would like to see you guys one time before we head off to summer. All right, take care, and let me know if you have any questions this week as you practice this stuff. And get ready for your last quiz on Friday. And don't forget, there's also going to be a Schoology formative for you on Wednesday. All right,